Hello everyone and welcome to lecture. Today's lecture will be about the partial derivative and various other aspects and ideas related to the derivative of a multivariable function. Specifically, we'll talk about the differentiability and what defines a differentiable multivariable function. So we'll start the lecture by defining the partial derivative. And luckily enough, if you recall from Calculus 1, the definition of the single variable derivative, you'll be very, very happy to know that the partial derivative extends directly from that idea. So if you remember back in 1D, the derivative of a function, also sometimes called the rate of change of a function at a point, is essentially the slope of the tangent line at that point. So let's say this is our function. Looks like this may be the derivative at any point x naught, or we'll say this is the x-axis, this is the y-axis, and this is the curve y equals f of x. The exact mathematical definition of the derivative is that it's the limit as delta x goes to 0 of f of x plus delta x minus f of x naught. Oh, this needs to be x naught divided by delta x. And this is very, very commonly said to be f prime of x naught. Another possible notation for this that's very common is dy dx at the point x naught, to indicate that this is being evaluated at the point x naught. So you'll remember that this idea essentially gives us the slope of what's said to be the tangent line of the function at a given point. So the slope of that tangent line, or the linear approximation of a function at a point, is exactly this limit. The reason being that if you look at this difference quotient that you're looking at right here, this difference quotient for any delta x, say between x naught here and x naught plus delta x, this difference quotient is the slope of what's called the secant line, or this line right here, the line between this point and this point. And as delta x gets smaller and smaller and smaller, this secant line approaches the tangent line to the function at a point. So if the function is differentiable at a point, then we say that this limit exists, and the function is best approximated by this tangent line local to the function, or around the point x naught. So local to the point x naught. We can almost directly extend this idea to define the partial derivative of a multivariable function. And in this lecture, I'm just going to consider a multivariable function of two variables, but hopefully you can clearly see once you watch the lecture that this extends to a function of any number of variables. We can actually extend this idea to functions of 3 variables, 4 variables, really any number of variables that you want to consider. So we define the x partial derivative of a function f as follows. And the notation is a little bit, it's similar to single variable calculus, but the notation is also a little bit different. So we actually introduce a new symbol called the partial derivative symbol to denote the partial derivative of a function with respect to x being evaluated at some point. This is now a point in 2 dimensions for a function of 2 variables, r naught, where r naught is just the vector x naught, y naught, just some point in 2D space. So we say that this is equal to the limit as delta x goes to 0 of f of x naught plus delta x comma y naught minus f of x naught comma y naught divided by delta x So it's very, very similar to how we define the single variable derivative for a single variable function. Is that the partial derivative is the single variable derivative in the direction of the coordinate x. What that means is that we also have, for a function of 2 variables, we have 2 partial derivatives. We have a partial derivative in the direction of x, and we have a partial derivative in the direction of y. And we say that if both of these limits exist, then we have existence of both partial derivatives. Or if only one of these limits exists, then we only have that one of the possible partial derivatives of the function exists. But you can see that for a function of 2 variables, we have 2 separate partial derivatives that in general give separate values. For a function of 3 variables, then you'll have 3 partial derivatives, an x partial derivative, a y partial derivative, and a z partial derivative, and so on and so forth for really any number of variables. For a function of 5 variables, you'll have 5 partial derivatives that correspond to the each individual component of that function. The key takeaway here for us is that really the definition of these partial derivatives is based on the limit definition of the single variable function, and because of that, right, when we go and calculate, say, the x partial derivative, we can use all of our derivative laws from single variable calculus. So the product rule, the chain rule, the quotient rule, all of the derivative laws hold. In the only thing that we have to remember here and kind of take away from this equation is that when we go to take the x partial derivative, we treat y, the other variable, as a constant, because it doesn't change at all when you're only taking the x partial derivative. Same thing for, say, the y partial derivative. You can take when you're taking the y partial derivative, you treat x as a constant, because x isn't changing if you're only evaluating the rate of change of a function in the y direction. So this is going to be a key point when we go through and do some examples for calculation of the partial derivative. So it's also important to write down that we have some notational, like some other separate notations for the partial derivative. And these vary across sources, but there are a couple of common ones that are important to denote. So The first one is the fractional notation, a df dx or df dy. And I'll probably put df dy over df dx. And I'll just put an equal sign between these multiple different notations. So df dx at a given point r naught, or df dy at a given point r naught. This is the same thing as we can use what's called subscript notation. So you could say fx at the point x naught y naught, or fx at the point r naught. Same thing for the y partial derivative. This is sometimes called subscript notation for the partial derivative. Another common notation would be if, say, you have that the output w is equal to f of x y. You could also use this and say that this is the same thing as dw dx at the point r naught, or dw dy at the point r naught. But these are the two very common notations that we'll see and we'll use a lot when we're talking about partial derivatives of a function. The subscript notation and the fractional notation. It's also worth pointing out that in terms of computation, right, and I mentioned this before, but I want to kind of emphasize this again, just so that everyone listening is clear. In terms of computing this partial derivative, so the x partial derivative and the y partial derivative, all of our computational rules from single variable calculus apply almost directly to computing partial derivatives. So you want to kind of brush up on all of your single variable calculus derivative rules, the product rule, the chain rule, the quotient rule, because really this right here is the same thing. The x partial derivative is the same thing as the normal single variable derivative, the x derivative of f as a function of x and fixed at y naught. This is evaluated at x naught. And the y partial derivative is the same thing as the normal single variable derivative of the trace f of x naught y at the point y naught. So this is like saying, if you consider to get the x partial derivative, you can consider the trace of the function at y naught, and this is going to taking the normal single variable derivative of the trace at y naught will give you the partial derivative. And same thing for the y partial derivative, that the y partial derivative at any point will be the normal single variable derivative of the trace of the function f along the point x naught. And we'll see what this corresponds to graphically a little bit later on in the lecture for one of our examples. But what I want to do is try to visualize this for functions of two variables. Now again, it's harder to visualize for a function of 3 variables or 4 variables, so we're going to stick with the function of 2 variables, because we can visualize the graph of a function of 2 variables very nicely in 3 dimensions. So for our visualization, what we're going to do is we're going to kind of draw our 3 axes, the x-axis, the y-axis, and the z-axis. and get an idea about what the calculation of the partial derivative is saying at any given point. So what we'll do is we'll consider the following points. Let's say for argument's sake the function is takes on maybe this value here, this z value here, this z value here, and then this z value here. And the surface looks like this on the boundaries. So this is our surface, z equals f of xy. Maybe it comes up like this and then goes down. And same thing here. Suppose it comes up like this. Kind of goes down to that. So these are, say, two traces of the function. A trace at the point x naught right here. So we'll say at this point right here. And this curve right here corresponds to a trace of the function at some value y naught in the domain. So that's this trace right here. So they intersect right here at this point right here. So this value, the z value of the function at this point, this is our point r naught, is x naught, y naught, and it maps up to this point, this z value, where this z value is given by z naught and is equal to the value of the function at x naught, y naught. So like we showed before, and I was talking about before, that the trace of this function, the derivatives of the traces of this function at a given point is the same thing as the x partial derivative and the y partial derivative. So at this point, the x partial derivative is the slope of the tangent line to this, the trace at y naught, which is the slope of this line right here. And the y partial derivative is the slope of the trace of this tangent line right here to the function. So you see a nice kind of clear picture about what these partial derivatives are representing if you graph them out in 3D. And what we're going to see is that the correct way of defining differentiability of a multivariable function is having, in some sense, the existence of this tangent plane. So you see here that both of these tangent lines form a tangent plane, it's called, or a plane that is tangent to the graph of this function. You can visualize this really at any point on this surface, or on a function who has a kind of smooth surface. You can visualize this tangent plane to the function, and you see that if you kind of move around to different points, the tangent plane is going to be it's going to have a different slope in different directions, in the x direction and the y direction. But the idea is that this tangent plane for a multivariable function of two variables is the same concept as the tangent line. So existence of a nice tangent plane is going to lead to differentiability for a function for us. For functions of more than three variables, this concept is the same, only it's harder to visualize. We can't visualize a tangent plane in 4 dimensions, say, for a function of 3 variables. But the idea is that we can still define differentiability via this tangent plane, via what's called the linearization of the function. So in some sense, this tangent plane is a linearization of this function around the point, so around this point. If you get very, very close to the point, in regions very, very close to the point for differentiable functions, the linearization should be a close approximation to the actual function. And this is the idea, the really big idea behind defining differentiability of a multivariable function. But the main idea here is that the main takeaway from this is going to be that partial derivatives are used to define what's called the tangent plane and more generally what's called the linearization. Also known as the linear approximation. To a multivariable function. At some point. So these are ideas that we will get into a little bit later on, but really we want to kind of think of these partial derivatives as being the rate of change in each individual direction. So the rate of change of the function that we're talking about. So let's go through some examples. And we'll go through 3 examples of how to compute these partial derivatives. And again, I'm only going to focus on functions of 2 variables, but all of these things apply to functions of any number of variables, and including the limit definitions that you saw earlier. So let's consider the function (5x squared plus 4xy plus y squared). The x partial derivative of this function f at any point is going to be computed by taking the x derivative of this expression and keeping y constant. So this is going to be 10x plus 4y plus 0 and we computed that using the power rule here, and again the power rule, the derivative of the function x is 1, and you have to treat 4y as a constant because you're taking the x partial derivative here. And then lastly, if you're treating y as a constant, the x partial derivative of y squared is just going to be equal to 0. Likewise, df dy is going to be 0 plus 4x plus 2y, which is just 4x plus 2y. And again, this is computed using the fact that x is constant with respect to y. So the y partial derivative of 5x squared is 0. The y partial derivative of 4xy, well, the derivative of y is 1. And we're treating x as a constant, So the derivative of y is just 1, which leaves us with 4x. And then the derivative of y squared is 2y. So these are the partial derivatives for this function. We'll consider a slightly more complicated example. Let's do the function g of xy is equal to e to the negative x squared plus y squared. The so-called bump function, if you look at the graph of this in 3D, by doing the traces of the function, you'll see that this function looks like kind of a bump at the origin. We've seen this before. It has circular level curves, and it's exponential as a function of x and y. So I'll use the other notation here just to kind of show that you can use either notation. Gx as a function of x and y is going to be equal to the x partial derivative of this function, which we're going to have to use the chain rule here. So the x partial derivative of the chain rule, where we're keeping y constant, is going to be e to the negative x squared plus y squared multiplied by the x partial derivative of this function right here, which is going to be negative 2x. So this is just applying the chain rule from single variable calculus, that the derivative of a function composition is the derivative of the outer function, which is this, times the derivative of the inner function, which is negative 2x. So our result is that gx, the x partial derivative of the function g, is the function negative 2x times e to the negative x squared plus y squared. And here's where I want to mention that there's a little trick that you can sometimes do for calculating the y partial derivative, and this has to do with the symmetry of the function. So if your function is symmetric, which not all functions are, but this function is symmetric with respect to x and y, which means if I replace g of xy with g of yx, so at any given point I swap where x and y are. This is the function e to the negative y squared plus x squared. And not all functions are always equal to the original function when you swap x with y, but you see that this function is. So if you switch x with y in this function, the function is completely symmetric. And what that means is that when you go through and calculate the y partial derivative of this function, the y partial derivative is going to be the same as the x partial derivative, but with x and y swapped. So this is going to be equal to negative 2y e to the negative x squared plus y squared. And you'll see that I didn't even have to go through and do any calculations for this y partial derivative. I can just use the fact that this is a symmetric function of x and y and use my previous calculations for the x partial derivative. Now this may not seem like a huge deal for this example, but we'll see in the next example that this is a very, very big idea. It allows us to get very, very fast, quick derivative calculations if we have a symmetric function. I recommend going through and actually using your derivative laws to get the y partial derivative as well, because it's good practice. But I'm going to leave this example here. So we'll call the previous example was example 1. Just number these in bookkeeping. We'll call this example example 2. And we'll consider a third example now. So for the third example, we'll look at the function h of xy is equal to x times y times e to the negative x squared plus y squared. So it's slightly similar to our other computation, or to our other function, a little bit more complicated. dh dx, the x partial derivative. When we look at this, we see here that you have a function of x and y, and specifically, right, we're treating y as constant when we take the x partial derivative. So this is going to be equal to the same thing as it's the function y times x times e to the negative x squared plus y squared. And so what you see here, we're going to have to apply both the product rule and the chain rule to get the x partial derivative of this function. The first one we're going to have to apply is the product rule. It's going to be derivative, x partial derivative is going to be y times the derivative of x, which is 1, times e to the negative x squared plus y squared, plus x times the derivative of e to the negative x squared plus y squared, which we calculated before from the chain rule is negative 2x e to the negative x squared plus y squared. So this was first we did the product rule here, and then we had to do the chain rule. We can simplify this a good deal by factoring out e to the negative x squared plus y squared to get that dh dx is equal to y times 1 minus 2 x squared times e to the negative x squared plus y squared. And this will be our final result for this partial derivative. And here's where you can hopefully see that our symmetry rule from before comes in very, very handy, because this function is symmetric with respect to y and x. If you plug in x where y is and y where x is in this function, you get the same function. So h of xy is equal to h of yx. And what's nice about this then is that if you don't want to compute the y partial derivative, you don't have to. You can rely on symmetry. So by symmetry, dh dy is going to be equal to x times 1 minus 2y squared times e to the negative x squared plus y squared. Because the function h is a symmetric function of x and y. Now it's important for me to emphasize here again that this is not always true. You know, the example 1 is an example of a function that's not symmetric as a function of x and y. But this function is symmetric, and therefore we can use this trick. So in a second, I'll open up a visualization so we can kind of see that this is giving us, a very, it's giving us exactly the tangent plane and those two tangent lines that we were talking about before. But let's just go through and we'll use these two formulas to give us, a computation. So specifically, we'll evaluate these partial derivatives at the point r0, x0, y0, where x0 is equal to -1, say, and y0 is equal to -3/2. So we're going to evaluate the partial derivative at this point. So using the above equations, we have that hx at the point -1, -3/2 is going to be equal to y, which is -3/2, times 1 minus 2 times x squared. X is -1, times e to the -1 squared plus -3/2 squared, which is the same thing as -3/2 times 1 minus 2, which is -1, times e to the -1 plus 9/4, which finally simplifies to just 3/2 times e to the -13/4. So the x partial derivative of h at the point -1, -3/2 is directly given by this value. This is exactly the slope of the x trace at y equals -3/2. Furthermore, if you go through and get hy at this point, you'll see that hy, or the y partial derivative of the function, on the trace for x equals -1/2 is equal to 7/2 e to the -13/4. And you get this by doing what we did before, which is plugging in of the absolute value for y x minus y, -1 and -3/2 into the equation minus the absolute value that we obtained before for dh minus the absolute value of y. So what I'm going to do right now is run my Python code at the point x0, show us a plot of this function, and I'll also show the level curves in the density plot of this function, so we can kind of see the limit definition of the partial derivative. This is going to be the limit, sort of describing what this function is doing. X goes to 0. In the specific figure that we're interested in here is at the first figure over here, which is 0 figure on the left, which is the plot of the graph of the function, minus f at 0, 0. So you can see that this function has over two what are called local minimum, 2 local maximum. It also has a saddle point, it looks like, at the origin. So it's like a saddle looking function. Remember, here. This is, we're just looking level here curves are both circles. R0. And they're also, hyperbolas as well. I want to call this R0. And this is a vector, so you got to put an arrow over it. And you can see that at the point -1, -3/2, as delta x goes this point right here, the x partial derivative
when y is 0
is given by
both
this
these
line
cases,
right here,
so
which is
zero,
a little
this
bit
is
faded,
0.
but it's
For this
a
first case,
green
it's just
line,
going to be f of
and then the y partial
delta x,
derivative
comma,
is
0,
given by the orange line,
which will be the absolute value of
delta x minus the absolute value of delta x, which is this line right here. And both of these lines are
delta
tangent to the surface of this function, x times y times e to the negative xy squared
to 0.
And you can also see that these two tangent lines
over delta
form
x,
a tangent plane
which is equal
to the
0.
surface of this function at that point. And for any other given point that
So the
you
partial
evaluate
derivative
these partial
exists
derivatives
for this
at,
function.
you're going to get a similar picture.
And
If
at
you
the point
plot
0,
out
0, it's equal to 0.
the tangent plane
A similar
and the tangent
calculation
lines
for the y
along
partial
the
derivative at
traces
this point.
at any point. So
That will
we're going
conclude
to see
today's
how
lecture.
to
Thank
generally
you very much
get
for
this tangent plane, and for any function, solve for this tangent plane, regardless of what the function looks like. Before we do that, I want to introduce what's called the gradient vector, because this will be a very, very big tool for us going forward. So the gradient vector, or the gradient vector field, is what's called a vector field, or a collection of vectors at any given point. Remember that a vector at any given point is, you can think of it as like a directional arrow at any given point. But the idea behind the gradient field is that once the partial derivatives of a function are taken, we can store that information in a vector. This vector is called the gradient vector. And the gradient vector has the following notation. We use an upside down triangle to denote the gradient vector, and we put it to the left of the function that we're taking the gradient vector of. So for example, in 2D, where we have two partial derivatives with respect to, say, x and y, the gradient vector of a function f is just the collection of the x partial derivative and the y partial derivative. And if you've ever taken a linear algebra course, or maybe plan on taking a linear algebra course, we'll see there's a typical reason that we write this as what's called it's a two-column, one-row matrix, or a 1x2 matrix. But in 3D, the gradient vector is the collection of all three partial derivatives of the function. So it's the collection of the x partial derivative, the y partial derivative, and the z partial derivative. So in 2D, it's a function of two variables. In 3D, we're dealing with functions of three variables. You can do the gradient vector in the partial derivatives for any number of variables, for a function of any number of variables. But the reason that we call it a field is that at every given point we have a different value for the partial derivatives. So the partial derivatives in general are functions of position, of space. So the gradient is also a function of position. At any given point, this gradient vector is changing. So because of that, we call it a gradient field. So this collection of vectors has extreme physical significance for any given multivariable function, whether it's the multivariable function is describing temperature or height. One of the things that we'll prove eventually when we get to what's called the directional derivative is that at any given point, the gradient vector points in the direction of fastest increase of the function. So we will show when we get to the directional derivative that the gradient vector always points in the direction of maximum increase of the function f. So just going back to our examples to kind of show you what the gradient vector field looks like and why it's a field. Right, for example, 1, say, the derivatives that we calculated were 10x plus 4y. So the first component of the gradient vector is going to be 10x plus 4y. The second component of the gradient vector will be 4x plus 2y. This is a y partial derivative. So this is what the gradient vector looks like for the function from example 1. For example 2, I think we use g. The gradient of g will be the function negative 2x e to the negative x squared plus y squared, and negative 2y e to the negative x squared plus y squared, which we can simplify using some of our vector algebra from a previous calculus course. This is the same thing as the vector negative 2x negative 2y multiplied by the scalar function e to the negative x squared plus y squared. This is just a simpler way of writing this gradient. And then for example 3, look at the gradient of h. We found that this was 1 minus 2x squared times y times e to the negative x squared plus y squared, and 1 minus 2 y squared times x times e to the negative x squared plus y squared, which is the same thing as 1 minus 2x squared times y, comma 1 minus 2 y squared times x all of this times e to the negative x squared plus y squared. So these are the gradient vector fields for each one of these examples. And you can see why it's a vector field, because it depends on what point x, y you evaluate it at. It's changing at every different point that you evaluate it at. But if we open up the plots from before, now I'm just going to open up the density plot and the level curve plot. So this plot right here, the top plot, which is the level curve plot, and the bottom plot, which is the which is the density plot. The top plot here is a level curve plot. And what you can see on these two plots is that the arrows here, these black arrows, I've plotted the gradient field at every single given point here. So what you can see here is that at any given point, say maybe at this point right here, the value of the gradient is pointing uphill. It's pointing in the direction of fastest increase of the function. And at points where the function is decreasing or going down, it's also pointing away from the minimum of the function, the lowest value of the function. So we're going to actually prove this in general. This is going to be, but you can visually see that if you look at these vectors at every given point. So here you can directly see how for a given function, the gradient vector is telling us a lot of information, the gradient vector field, about how the function's increasing and decreasing at a given point. So more on that a little bit later on in the course. So what we want to do is define multivariable differentiability, what it means for a multivariable function to be differentiable. And it turns out that the existence of the partial derivatives is in fact not enough to define multivariable differentiability. And we'll see why in an example shortly. But in motivation for the definition of differentiability, we're going to go back to 1D and look at what it means for a function to be differentiable, or for the derivative to exist in 1D. And in general, this is we'll call this differentiability of a multivariable function. So if we remember back to the definition of differentiability in 1D, a function is said to be differentiable at a given point. Say, we'll say this point x naught, say. If the derivative of the function f at x naught, this limit as x goes to or as delta x goes to 0, of f prime of x naught plus delta x minus f of x naught over delta x. Oops, gotta erase this right here. It's if f at x naught plus delta x minus f of x naught over delta x, if this limit exists. And what this means is that the slope of the tangent line, or the linearization of our function, the best linear approximation of our function, is exactly this right here. It's the tangent line of the function, which is the function L of x or which is f prime at x naught. I'll actually start with f of x naught. It's f of x naught plus f prime at x naught times x minus x naught. So the tangent line, remember, of a function f at a point is exactly f of x naught, which is the y-intercept of that tangent line, or sorry, the x naught intercept of that tangent line. It's exactly this. When x equals x naught here, right, the height of the function is f of x naught plus m times, so it's the slope of the function times x minus x naught. So the slope of this tangent line is exactly f prime. But if this limit exists, then this L of x is the best linear approximation to the function at the point. And what this basically means is that if you look very, very, very close to the point, so say you go to x naught plus delta for some delta, and x naught minus delta, so in a very, very small interval around this point, and think of delta as being very, very, very small here, the value of the function, the smaller delta gets, is closer and closer and closer to the value of the linearization, the tangent line. So for example, you can look at, we'll look at two separate examples from 1D, right? A function that is very, very nice and differentiable at every point. We'll look at f of x is equal to sine of x. And this is differentiable at every point, but we'll just look at the origin. So remember, if you remember, sine of x looks like this. I think I can do better than that. So this point is negative pi over 2. This point is pi over 2. And if you look at the tangent line to this function, which we'll do in blue just like above, the tangent line to this function is this line right here at this given point, the slope of which is given by the derivative f prime, which is just cosine of x at the point 0. F prime of 0 is cosine of 0 or 1. So the slope of this function at this point, the slope of the tangent line to this function at this point is 1. It's differentiable, and the closer you get to the function, the closer this tangent line approximates the function. So the tangent line, this tangent line is exactly given by L of x, which is f prime of x, x naught, plus the value of times x minus x naught plus the value of the function at x naught. So it's going to be sine of 0 plus cosine of 0 times x minus 0, which is just 0 plus 1 times x minus 0, which is equal to x. And this is what allows us to say that for very small values of x, so when x is much less than 1, sine of x is approximately equal to x. This is where this approximation is coming from, and this is used very often in physics. But this is we can do stuff like this because the reason we can do stuff like this is because sine of x is a differentiable function at this point. So its linearization at any given point is approximately equal to the value of the function at the point. If instead you consider a different example, we'll use the standard example in most Calc 1 classes for a function that's not differentiable, and that's the absolute value function. We'll do that right here. This is just I'll label this. This is a differentiable example. Our function that's not differentiable, we'll look at f of x is equal to the absolute value of x. Now remember that the absolute value of x looks like negative x for negative when x is negative, and it's the function positive x when x is positive. And you can show using the limit definition of the derivative that the limit from the left-hand side of that difference quotient or the limit as delta x goes to 0 from the positive side of the absolute value of 0 plus delta x minus the absolute value of 0 over delta x. The same thing as the limit as delta x goes to 0 from the positive of the absolute value of delta x over delta x. This limit is equal to 1. So this is saying that the derivative of this function from the derivative of this function on the left side, sorry, the right side of the point x equals 0, x naught equals 0, is 1. But if you do this exact same limit from the left-hand side, where the limit as delta x approaches 0 from the negative side, where delta x is negative, the derivative of this function, the limit for the derivative of this function is going to be the limit of 0 plus delta x minus the absolute value of 0 over delta x, which is the limit as delta x goes to 0 from the negative of the absolute value of delta x over delta x, which is equal to -1. So that's saying the slope of this function on the left-hand side of this function is -1. So this function is not differentiable at the origin, at x equals 0. And what that means is that there's no nice tangent approximation of this function. And for any tangent line you try to draw here, or any linearization you try to draw here, the better you approximate the right-hand side with your linearization, the worse the approximation is going to get on the left-hand side. And vice versa. If you try and approximate the left-hand side with a given linearization, the approximation on the right-hand side is going to get horrible. So this is really what differentiability is. It's the lack of a linearization or a tangent, approximation to the function. So this is what it is in 1D, and this is the idea that we're going to have to take with us for multivariable functions as well. And with this idea in mind, it becomes possible to define the differentiability of a multivariable function. So just remember, this is an example right here of a function that's not differentiable. At x equals 0. This is an example of a function that is differentiable at x equals 0. So for multivariable functions, we say that, and we're going to do this for a function of 2 variables, but it can be directly extended to a function of 3 or 4 or any number of variables. We use an almost exactly similar condition. Say that a multivariable function is differentiable if there is a best linearization or linear approximation to the function. I should say here, a differentiable at a point are not if there is a best linearization to the function at that point. For functions of 2 variables, this is the same as saying there exists a best tangent plane to the function that locally approximates the function, or you can define the tangent plane at a given point. So for a function of 2 variables, we say that and we'll do this first, so 2D, the linearization is given by, we'll call it L of x comma y. This is the linearization of a function of x and y. L of xy is equal to the value of the function at the point x naught y naught, or at r naught, plus df dx at r naught times x minus x naught plus df dy at r naught times y minus y naught. And we say this is a tangent plane because we can call this right here, say, the z-intercept of a plane, this value right here, the slope of the plane in the x direction, and this right here, the slope of the plane in the y direction. And if we write down the equation, z is equal to the linearization at a given point, then z is equal to m times x minus x naught plus n times y minus y naught plus this b, or you can say z naught. You can use b if you want to use b, but I'm probably going to write z naught here because that's just relating it to the function f. And this is the equation of a plane centered at the point x naught, y naught, z naught. Or that this plane is exactly the tangent plane if these partial derivatives exist. So we can use this, and we'll see how to use this to define, an approximation of a function. If you say want to approximate a given function z, right? The value of a function, or the value of f for points that are very close to x naught, y naught, say, if a function is differentiable at a point, so this linearization exists and it's a good approximation around a point, if you kind of zoom in very close to the point x naught, y naught, so in this region right here, when you're like very, very close, say within delta, where delta is a very small value of the point x naught, y naught, then the value of the function inside this region, we'll call it D, is approximately equal to this linearization. Which means that f of x comma y is approximately equal to f of x naught comma y naught plus df dx times x minus x naught plus df dy times y minus y naught. This is what differentiability is telling us. If a function is differentiable, then when you get very close to a point, the value of the function is approximately equal to the value of the linearization at a point. And this idea holds for any functions of any number of variables. So we'll see how to use this in examples a little bit later on. I definitely do want to just write down, though, what happens for the linearization for a function of 3 variables or any more number of variables. Let's say you have a function g of x, y, and z. Okay, then the linearization for a function of 3 variables is going to be found in the exact same way. It's equal to the function, we'll say the linearization at the point r naught in 3D, which is x naught, y naught, z naught. It's the value of the function at x naught, y naught, z naught plus df dx at this point r naught times x minus x naught plus df dy at the point r naught times y minus y naught plus df dz the point r naught times z minus z naught. So you can hopefully see how this would be extended to a function of any number of variables. The linearization or linear approximation of a function extends for any number of variable functions. And we've seen a couple different functions that we can now, using this idea of linearization and tangent plane, form the linearization of. Because all of the functions in example 1, example 2, and example 3 that I showed are very nice functions. What I want to end with is an example of a function that is not differentiable. This is called the roof function. And its function, we'll use the roof function of two variables. It's going to be similar, very, very similar to the absolute value function in the single variable case. So this is, put a warning first. Existence of partial derivatives does not guarantee differentiability. So just because you can calculate the partial derivatives at a point doesn't mean that the function's differentiable there. This roof function is a great example. So the roof function is f of xy is equal to the following. Absolute value of the absolute value of x minus y minus the absolute value of x minus the absolute value of y. And we'll look just at the origin. So at the point x naught is equal to 0, 0. So from the limit definition of the partial derivative, this is going to be the limit as delta x goes to 0 of going to be f at 0 plus delta x comma 0 minus f at 0, 0 over delta x. So remember, this is, we're just looking here at r naught. Oops, not x naught. I want to call this r naught. And this is a vector, so we got to put an arrow over it. So this is the same thing as the limit as delta x goes to 0 of, well, when y is 0 for both these cases, so this is 0, this is 0. And then for this first case, it's just going to be f of delta x comma 0. This will be the absolute value of delta x minus the absolute value of delta x over delta x, which is just equal to the limit as delta x goes to 0 of 0 over delta x, which is equal to 0. So the partial derivative exists for this function, and at the point 0, 0, it's equal to 0. A similar calculation for the y partial derivative at this point is going to be that the y partial derivative also exists at the origin and is also equal to 0. But if we open up a plot, I use my Python code to plot this function, we'll take a look at what this looks like and why this function is not differentiable. And let me do the following. I'm going to take off. So I still have the tangent plane plotted. We can probably keep that up. So we'll rotate our function and we'll just ignore the tangent plane there that I plotted from before. So this function right here, if you look at it, it clearly has an x partial derivative and a y partial derivative at the origin, and they're clearly 0. So the derivative here is 0, but the x partial derivative in this direction is 0. The rate of change is 0 along the x-axis. Same thing along the y-axis of the function. That's equal to 0. But, so this is 0, the slope here, and this is 0 right here, the slope here. But you can see that this is, along either direction, say at any point here, you have this cusp kind of going along, and same thing, a cusp here. That's why we call it a roof function. And around this point, the origin, there's no nice tangent plane approximation of the function. You always have a lot of error in the tangent plane approximation of this function. The tangent plane here is just the xy plane, and no matter what path of approach you take, the tangent plane will never be a good approximation of the function at this point. So this function is not differentiable. That will conclude today's lecture. Thank you very much for listening, and I hope you learned something and had a great day.